Okay, let's try again. So we are well into chapter 4. Hopefully you guys were able to practice a little bit with nomenclature over the weekend. It doesn't sound that promising. Hopefully some of you had some time to practice nomenclature and found out it's really not as bad as it may look. It's ultimately just knowing those rules and applying the rule consistently every single time. Okay? There's a couple extra wordings that came up when I went back through and reviewed saplings, so I wanted to make sure you guys were aware of that. A lot of the common names, or some of the common names, have kind of weird roots. The iso group is the one that we talked about last week, and so it's that shape that I've got highlighted in red. If we've only got 3 carbons in our substituent, then we'll name it propyl for those 3 carbons. So with that shape and 3 carbons, we get isopropyl. When we move to 4 carbons, we can still generate that same shape, but now in the overall structure, we got 4 carbons, so that's where we get our isobutyl. The last 2 on that 4-carbon sequence that I think make the most sense to me is looking at the sec-butyl and the tert-butyl groups. So in both those cases, we're looking at 4 carbons, and we're looking at where these functional groups attach to the main chain. So that's our hanging now red bond. That's where it would attach to the main group or the main structure. With the sec-butyl group, what we're saying is that it's attaching at that carbon, and that carbon happens to be a secondary carbon, hence the term sec-butyl, sec for secondary. If we go through and take a look at the tert-butyl, again, where it's attaching to the main chain, that carbon is a tertiary carbon, so we get tert-butyl. Okay, so it's just the shorthand for tertiary. You'll typically also see it referred to as T-butyl, okay, and that will continue to pop up. That's, in general, kind of a favorite functional group shape. Shows up in a lot of different cases. So it might be helpful to know what secondary, tertiary, what those terms mean. So what you'll probably see are primary, secondary, tertiary, and potentially quaternary, though much less frequently do we look at quaternary. What those are referring to in the case of alkanes is the number of carbons attached to the carbon that we're looking at. Okay, so a primary carbon, so if we were going to draw this out, a primary carbon, so there's our single carbon, is only attached to one other carbon. And that means the rest of it has hydrogens. So our red carbon in that case is a primary carbon. If we move to a secondary carbon, we're looking at it bonding to 2 other carbons. Tertiary bonding to 3 other carbons. Whoops, I've been color coding them. And quaternary, we're looking at a carbon bound to 4 other carbons. Why do you think the quaternary is very seldom evaluated? It's buried inside a covalent bond structure, which we could say was similar to hydrogen, but hydrogen and carbon do have a slight difference in electronegativity, so we can generate some reactivity there. The carbon-carbon bonds are so nonpolar covalent, they're very unreactive. Very rarely do we ever look at a quaternary structure other than to call it quaternary. That's about it. When we look at the sec-butyl and the tert-butyl, remember these are carbons that are attaching to a longer chain. So if we real quickly drew a jagged, let's say that's just a bunch of carbons there. How would we reference that carbon that's attached? Is it primary, secondary, or tertiary? Interesting question. It's tertiary. It's attached to the main chain as another carbon. Okay? Why do we call it sec-butyl? We've already counted the main chain in the rest of the name. Okay? So that won't count towards naming that as a tert-butyl group. It's a sec-butyl group. Okay? Kind of an odd little system there. Knowing the origin of those names isn't all that big of a deal. You ultimately just need to know them. They do pop up every so often. You will see them for sure in sapling. You'll see them in your textbook. And as far as your final exam goes, the ACS test, I think they do occasionally show up there as well. Okay? These are the most common of the common names that you'll see. Remember, we talked about how we could name them via IUPAC, and everybody seemed to unanimously hate that version of it. But you could go through and name those substituents in that fashion as well. Okay? You are officially responsible for both, though primarily IUPAC. When it comes to the exam, at least the normal exams, if you've got a question about naming, feel free to ask, raise your hand, I'll come take a look at it. And if I think it's something that you should know, I'll tell you, sorry, I can't do anything for you. Otherwise, I'll draw it up on the board and write that extra information there. Okay? Questions about common versus IUPAC? Okay. So nomenclature of rings, as we already kind of alluded to when we looked at our ring structures, the naming changes a little bit. If we've decided that our ring is the primary functional group, we will name our main chain after the ring. Okay, so we will only count the carbons within the ring as part of our name. Okay? So we'll count out those carbons and then name it as the appropriate structure. So cyclo to represent that it's a ring, however many carbons with our Greek prefix, and then the ane ending, at least at this point, for our alkanes. Okay? Sorry, I completely blanked. Let's look at those examples. No idea where I was going with that. If we tried to draw out the structure of cyclopropane, okay, cyclo first off means we're looking at a ring. How many carbons are in that ring? We've got 3. How are they connected? Well, at very least we get single bonds because it's cyclo. Do we have any double bonds in the structure? No. How do you know that? It just says ane. We could then go through and draw on our hydrogens. And we've got our cycloalkane. By the way, I do remember what I was going to say. How else could we abbreviate this? We could also go through and draw this out as just a triangle. Every point is a carbon. All those carbons have implied hydrogens to satisfy their octets. Okay. Whoops, I didn't want to erase that. Oh well, let's just erase everything. Let's go ahead and draw out the cyclobutane. What shape would we get there? We've got a square, or close enough to a square, which brings up another interesting point. Okay, eventually we'll have a square, in theory. So we've got that square shape. There it goes. How perfectly square should that be drawn? Those are all carbon-carbon single bonds, right? So they're all equivalent bonds, which means the bond length should be equal for all of those, which means how perfectly square should this be? Pretty darn close to a perfect square. Okay. We will see some shifting from that if you look at the energy of that structure, which we probably won't evaluate. But the main reason why I want to address this is that does it look like a perfect square here? It's actually not too bad. What if I'd actually change it around to looking like this? Okay, that doesn't look like a perfect square. Is that still cyclobutane? Yes. When you're trying to draw these structures, worry less about how good it looks, worry more about the content. Okay, make sure your content is correct, and then if you got time, particularly when it comes to an exam, go back and fix the structure to make it look a little bit more appropriate. Do you have a hand or a question? No? Okay. And because that just looks weird to me, I got to fix it. So the next part I was going to address was if we put on substituents. So we'll go through and add a couple. So we've got a cyclobutane with what as substituents? What I would go through is circle them and identify them. We have a methyl and we have an ethyl. Here's my primary weakness. If we were going to go through and now put this into a name, which substituent comes first? Ethyl, because alphabetical. So we would name it as ethyl methyl cyclobutane. Before we can call that official, we'd also have to specify the positions. Okay, hopefully you all did a little bit more reading than I did. Which one is position 1?
Methyl.
Why is the methyl position 1? What's that? What does the rule say? Because the rule is the part where I'm...
Start numbering at the highest priority.
So if the rule says start numbering at the highest priority, we start numbering at the ethyl. Ethyl will take higher priority than our methyl. When it comes to priority rules, those really make a large play in Chapter 5. We will talk about it. It's like the very last slide of the Chapter 5 slides. So if you want to look for those rules, you can find those in those Chapter 5 slides, which are posted. Okay? Along with the last 2 slides of Chapter 4. Wasn't paying attention. Thought it was going to be half, but it wasn't. So if we were going to go through and name this, we'd end up with our 1 ethyl, 2 methyl. Why not 4? We want the smallest sequence of numbers. So putting it all together, we'd end up with our 1 ethyl. Whoops. Started to make the exact same mistake. 2 methyl. And then our cyclobutane. Yes?
Where did you originally get the ethyl?
I just put them in there.
Okay.
I just put them in there as an example. Yeah. Okay?
How do you know that ethyl is the highest priority?
Priority has to do based on atomic weight. Okay? So if we look at the first atom off of each of those substituents, what is it? Carbon versus carbon. Is there a difference in atomic weight? No. So what do? Move to the next atom. Just like we did with acids and bases. If we don't find a difference, move to the next atom. So we can go out to the next atom. In our ethyl, we go out to a carbon. In our methyl, we go out to hydrogen. Which one has the higher atomic weight? Carbon. Which one has the higher priority? Ethyl. Okay, so it's only based on atomic weight of the atom. So again, I'm saying atomic weight. So look at the atom that's connected. Where you see the largest atom, that one's going to have your highest priority. Okay, when it comes to alkanes, at least. So let's take a look at a couple examples here. I think I'll go ahead and name one of them, and then I'll let you guys work on a few others. And if you got questions, you can raise your hand. Which one should I do? Upper left-hand corner? I think. No, lower right-hand corner. I think lower left. Man, I can't hear what you're saying. Speak up. Okay. So, lower left is what we're going to target. What's the first thing we should do? Find our longest carbon chain. All right, so we could just go through 1, 2, 3, 4, 5, 6, 7. Hopefully those red dots are showing up. Yep, so I could say 7 carbons. Is that my longest carbon chain? No, so we have to keep going through until we find our longest carbon chain. And just to be slightly obnoxious, oh, actually it's not all that obnoxious. There's our longest carbon chain. You'll notice that it branches off of the middle. Okay, so ignore your kind of X, Y, Z axes. You need to find wherever the longest sequence of carbons is. When it comes to naming alkanes, we will absolutely shift them off of that vertical line or that horizontal line because that's the tendency for most students, is just to read the horizontal. There is no up, there is no down, there is no spoon. This is organic chemistry. Find the longest possible chain you can. Okay? How many carbons is in that chain? Wow, I talked too long. Apparently you guys got that figured out. What's our Greek prefix for 9? We're looking at known or non. What's our primary functional group? alkanes, so we've got non-ane. Now here's where I would go back to the substituents and identify each of my substituents by again circling them. If you got different colors, you might as well use your different colors and try and identify each of those. I see 2 carbons, which gives me F. It's a substituent, which gives me the YL. I see 1 carbon, so I've got meth, and again the YL as a substituent, and then again I have another ethyl. Now I have to identify where those individual groups are located. All right, how are we going to go through and number? Left to right, right to left. We're going to go right to left because we want to use the lowest possible numbers. If we go through and number the other direction, we end up with larger numbers for our substituents. My methyl is located at which position? So I've got 3 methyl. Where's my first ethyl? And then 6. I can now go through and put this all together into a sequence. Usually I don't like writing these out because it takes up a lot of space. My handwriting is not the greatest here. What would I start with? The ethyl functional group, which number? 4, 6, di, because there's 2 of them, ethyl, and then we're what, 3, methyl, nonane. Kind of get it? You guys actually want to practice this here and now, or do you guys want to deal with this on sapling? You're going to see it a lot on sapling. I heard at least 1 here, so I'll give you a couple minutes to work on a couple others. Left-hand corner. Everybody's good with the name that's already up there? Can I erase that, clean up the screen a little bit? Too late. So what we're going to do is take a look at that upper left-hand corner, and we need to decide how we're going to name this structure to begin with. Okay? If you go back to your rings, what we want to do is decide whether we name it for a straight chain or a ring. If the ring contains more or equal carbons and or our higher priority functional group, then the structure is named for a ring as the primary group. Okay? If our substituents have more carbons than our ring, then we name the ring as a substituent on that larger structure. So when we go back to that first, why did that shift but not my screen? What the heck? So I'm going to guess the internet is having problems. So if we go back to that structure, I can't highlight anything at this point. What's happening with our overall structure?